Hi, this is Tzvi Rosen with another lecture in our online course in matrix theory. We saw last time what an inverse matrix is. We found the formula for the inverse matrix to a 2 by 2 matrix. In this week's lecture, we're going to be finding the inverse matrix for matrices of arbitrary size. Okay, so how do we do it? Given a square matrix A, how do we compute A inverse? And we can use this matrix A as our example matrix to work on. It's a 3 by 3 matrix. So what I know about the inverse, let's say it's B. Suppose B equals A inverse. So I know it's going to be a 3 by 3 matrix because it has to multiply by A to give the 3 by 3 identity matrix. Okay, and it will satisfy that equation. So I know that A times B is going to be equal to I3, which is the matrix that has 1s on the diagonal and 0s everywhere else. Okay, so if I knew how to solve a matrix equation of this type, where you have a product of two 3 by 3 matrices, and it gives you another 3 by 3 matrix, then I could figure out what B is, given that I know A and the identity matrix. Unfortunately, I don't have a great method for that. But one thing we do know how to do, so we know how to solve matrices of the type, I should say equations of type AX equals B, where X and B are vectors. Okay, where X and B are vectors, namely, we form the augmented matrix AB, and we do Gaussian elimination, or Gauss-Jordan elimination. On the augmented matrix. Okay, so how can we use that here? Well, I know that AB, another way of writing this is I could take A and then treat each of the columns separately. So let's call the columns C1, C2, and C3. Then the result of this multiplication is another 3 columns, AC1, AC2, and AC3. And so in our equation, AB equals I3, really we can focus in on that first column. And what we would have is A times C1 will be equal to AC1, or 1, 0, 0. And solving that equation using Gauss-Jordan elimination on the augmented matrix will give us the first column of our inverse matrix. Okay, so let's do exactly that. We will plug in this first column of the identity matrix to find the, so this will help us find the first column of B. Okay, so let's do it. We'll start by, we'll do standard Gauss-Jordan elimination. We're always trying to get those leading ones and then eliminating everything else in the columns of the leading ones. So we'll start by switching row 1 and row 3 because it's easier to go from -1 to 1. So what we get there is minus 1, 5, 4, 0. Second row stays the same. This row goes down here. Okay. Next up, we're going to multiply the top row by negative 1 to get 1 minus 5 minus 4, 0. And then the rest of the matrix stays the same. 2, 1, minus 2, 1. Okay, next up, we want to cancel out everything in the same row as our leading, in the same column as our leading 1. So we take minus 3 row 1 plus row 2, and minus 2 row 1 plus row 3. What we get is first row stays the same. Second row gets minus 3 plus 3 is 0. Minus 3 times minus 5 is 15, plus 0 is 15. Minus 3 times minus 4 is positive 12, plus 1 is 13. And we have 0 in the final column. And then minus 2 plus 2 is 0. 10 plus 1 is 11. 8 minus 2 is 6. And 0 plus 1 is 1. Okay. And next up, we have to get a leading 1 in the second row. So we multiply by 1 over 15. So we get 1 minus 5 minus 4, 0, 0, 1. 13 over 15, 0, 0, 11, 6, 1. Okay, and now let's take this to the next page. Okay, we want to use this second row's leading 1 to eliminate everything else above and below it. So we have 5 row 2 plus row 1, and minus 11 row 2 plus row 3. Okay, that gives us 1, 0. Okay, 13/15 times 5 is 13 over 3. Minus 4, which is 12 over 3, gives us 1 over 3. 1 over 3. This stays 0. And then we have 0, 1, 13 over 15, 0. And 0, 0. Minus 11 times 13 over 15 is minus 143 over 15, plus 6, which is 90 over 15, gives us minus 53 over 15, 1. Okay, and then to turn this into reducer echelon form, we need to get the leading 1 in the third row. So we take minus 15 over 53 times row 3. And we get top two rows stay the same. 1, 0, 1 over 3, 0, 0, 1, 13 over 15, 0, and 0, 0, 1, minus 15 over 53. Move these zeros over. Okay, and now our last step is to eliminate the entries above this leading 1. So we get minus 13 over 15, row 3 plus row 2, and minus 1/3 row 3 plus row 2 gives us 1, 0, 0, and then 5 over 53. 0, 1, 0, 13 over 53. 0, 0, 1, minus 15 over 53. Okay, and what that tells us is that this is the first column of A inverse. Okay. Well, that's the first column. How do we get the second columns and the third column? Using the same approach, but solving for AC2 equal to 0, 1, 0 and AC3 equal to 0, 0, 1. So we would plug in 0, 1, 0 here, then do our Gauss-Jordan elimination, and what we would end up with is something that looks like the 3 by 3 identity matrix here, and then over here we'll get the second column of the inverse matrix, and then over here we would get 0, 0, 1, do our Gauss-Jordan elimination, and get 3 by 3 identity matrix and the third column of our inverse matrix. Okay, and then we could take C1 from this page. So this will C1 from this page, C2 and C3 from these processes, put it together and get the inverse matrix. But problem with that is this will be a lot of repetition, because the Gauss-Jordan elimination is completely the same on the left part of the matrix where most of our choices are being made. The only differences would be in the vectors at the far right. So what we can do instead is augment this matrix all at once. We'll just put a copy of the identity matrix here. Okay, this corresponds to solving for C1 and C2 and C3 all at the same time. And when we do this, essentially we're starting with something that looks like A, I3, and we're going via Gauss-Jordan elimination to something that looks like I3, A inverse. Okay. So to state this formally, so Gauss-Jordan elimination turns the matrix A, I, N into I, N, A inverse, and this assumes that the matrix is invertible, assuming A is invertible. And this is pretty cool. It's an exclamation point, a couple of exclamation points. Because it gives us a way to invert the matrix using a tool we already have, Gauss-Jordan elimination. Okay, so let's go ahead and give it a try. Let's see if we can get the inverse matrix here using this approach. So we'll start with the matrix we wrote down up there. This is A augmented by the identity matrix. And we'll follow the same steps as we did when we were getting that first column. So we'll switch row 1 and row 2, row 1 and row 3. We'll get -1, 5, 4, 0, 0, 1. Second row stays the same, 3, 0, 1, 0, 1, 0. Then 2, 1, -2, 1, 0, 0. Okay, same process, minus row 1 gives us 1, -5, -4, 0, 0, -1. Okay, other rows stay the same. Okay. What's up next? Well, we need to cancel out the entries below the leading 1, so we get minus 3 row 1 plus row 2 minus 2 row 1 plus row 3. This should look familiar. It's the same step we did before. And we get 1 minus 5 minus 4, 0, 0, minus 1, 0, 15, 13, 0, 1. Now this is 3. In the last row we get 0, 11, 6, 1, 0, 2. Okay. So far, so good. Now, what do we do next? Well, we need to get a leading 1 in the second row, as we did before. So we take 1 15th row 2, and we get 1 minus 5 minus 4, 0, 0, minus 1, then 0, 1, 13 over 15, 0, 1 over 15, 1 over 5. And then the third row stays the same, 0, 11, 6, 1, 0, 2. Okay, and now we want to eliminate entries above and below the leading 1. So we get 5 row 2 plus row 1 and minus 11 row 2 plus row 3. Okay, and that gives us 1, 0. Okay, this again is 13 over 3 minus 4. This is 1/3. And 0 and 1/3 and 0. Then we get 0, 1, 13 over 15, 0, 1 over 15, 1 over 5. And in the last row we get 0, 0. 13 over 15 times minus 11 gives us minus 143 over 15, plus 90 over 15 gives us 53 over minus 53 over 15. Okay, and let's give ourselves a bit more room here. And then this gives us 1 and minus 11 over 15. And minus 11 over 5 plus 10 over 5 gives us minus 1 over 5. Okay. Okay, now let's bring this to the next page. Okay, the next step of Gauss-Jordan elimination here is to get a leading 1 here, so we need minus 15 over 53 times row 3, which gives us, okay, first two rows stay the same. Okay, last row, we scale this is now 1. And this is minus 15 over 53. This is positive 11 over 53. And then minus 15 over 53 times minus 1/5 is positive 3 over 53. Okay. Next, we have to eliminate the entries above this final leading 1. So we're going to have minus 13 over 15 times row 3 plus row 2, and minus 1/3 times row 3 plus row 1. Okay, starting with the top row, we have 1, 0. Then this gives us 0. And In the next entry, we have 5 over 53. Okay, the next entry is a bit trickier, but it gives us 14 over 53. The next entry is minus 1 over 53. Okay, as for the second row, we have 0, 1, 0, and then 13 over 53. Okay. Minus 13 over 15 times 11 over 53 plus 1 over 15, after some computation, comes out to minus 6 over 53. And minus 13 over 15 times 3 over 53 plus 1/5 gives us 8 over 53. Please check these calculations. Make sure I've got it correct. And in the final row, we already have our answers, so we get these. Okay, and so the result of all of that computation is that our matrix, our inverse matrix, is here. This is our A inverse. You'll notice that all of the entries have 53 in the denominator. There's a reason for this, which we won't learn in this lecture, but we will eventually learn. But we could summarize this also by saying A inverse is equal to, and then we could just pull out this 1 over 53, and we would have 5, 14, minus 1, 13, minus 6, 8, and minus 15, 11, 3. Okay, and together with that scalar in front, that would give us our inverse matrix. Okay. So this is our correct answer. Okay, well we were able to show that this is the A inverse, that when we multiply it on the right, we get our square identity matrix. But how do we know that when we multiply it on the left, we also get that? Right? Just because A inverse is the identity, does that mean necessarily that A inverse A is the identity? And it turns out it does. We can think about how it acts on a given vector v. So if we multiply v on both sides, we get A inverse v is equal to v. Well, look at what happens when we multiply both sides by A inverse on the left. Then we get A inverse v equals A inverse v. Okay. But we know that matrix multiplication is associative. So I can group these matrix multiplications in whatever way I want. Matrix multiplication means that this equation can be written as A inverse A applied to A inverse V is equal to A inverse V. Okay, so what did we do here? I plug in, I have some matrix, and I multiply. This is a 3 by 3 matrix. This is a 3 by 1 matrix, or a vector. And then this is the very same vector. So I multiply the matrix by some vector, and I get the vector back. And it doesn't seem to matter what the vector is, as long as it can be written as A inverse V. Okay, so if A inverse V can describe all vectors in your space, then we can say conclusively that A inverse A is also the identity matrix. Okay, so we have that AA inverse is the identity matrix, and A inverse A is the identity matrix. Okay, so we've done a 3x3 example with great difficulty. So let's be really masochistic and try a 4x4 example as well. I know you guys are always eager to see examples, so let's give this one a shot. So the first thing I see is I want this one entry on the top. So I'm going to swap these two. So first of all, to start, we want to set up our augmented matrix. Okay, so augmented matrix should look like AI4. Okay, so we have 2 minus 15, 3 minus 1, 1 minus 2, 0, 0, 4, 5 minus 3, 1, and 0, 30 minus 8, 3. Okay. So the first thing I want to do is get this 1 on top. Okay, and what I get, oh wait, the augmented matrix, it has the identity matrix here. So it's 1, 1, 1, 1, and then zeros everywhere else. Okay, now we can switch rows. So we'll start by switching these two rows, and we get 1 minus 2, 0, 0, 0, 1, 0, 0, 2 minus 15, 3 minus 1, 1, 0, 0, 0, and then the remaining two rows are the same, 4, 5 minus 3, 1, 0, 0, 1, 0, and 0, 30 minus 8, 3, 0, 0, 0, 1. Okay. As we always do with Gauss-Jordan elimination, once we have our leading one, we eliminate everything above and below it. So we're going to take minus 2 times row 1 plus row 2, and minus 4 times row 1 plus row 3. Okay. Let's copy this to the next page. Ooh. Okay, so what we get is same top row, minus 1 minus 2, 0, 0, 0, 1, 0, 0. Okay, and then the next row down, we get 0. 4 plus minus 15 is minus 11. Then 3 minus 1, since those are just zeros. This stays 1, this becomes minus 2, and the rest are zeros. Okay, as for the next row, we get 0. 8 plus 5 is 13. And then this stays minus 3 and 1 and 0 and minus 4 and 1 and 0. And then this we didn't have to add anything to, so it stays the same. 0, 30, minus 8, 3, 0, 0, 0, 1. Okay. Next up, we need a leading one in the second row. So we multiply by minus 1 over 11. Okay, and scaling, we get 1 and minus 3 over 11 and positive 1 over 11 minus 1 over 11 and positive 2 over 11. Okay, and now to eliminate the other entries in the same column as the leading one, we get 2 row 2 plus row 1 minus 13 row 2 plus row 1 and minus 30 row 2 plus, this should be plus row 3 and minus 30 row 2 plus row 4. Okay. So, doing that arithmetic, we get 1, 0, minus 6 over 11, 2 over 11, minus 2 over 11, 4 over 11 plus 1 over 11 gives us 15 over 11, 0, 0. Okay, the second row stays the same. 0, 1 minus 3 over 11, 1 over 11, minus 1 over 11, 2 over 11, 0, 0. And then in this row we get 0 and 0, and then we have 39 over 11 minus 3, which is 33 over 11, so this is 6 over 11, and positive 13 over 11, minus 13 over 11 plus 11 over 11 gives us minus 2 over 11. And next we have positive 13 over 11. And then we have minus 26 over 11 plus negative 44 over 11 gives us negative 80 over 11, I believe. 26 and 44 gives us 70. Minus 70 over 11. And then we get 1 and 0. And there's one more row, which is 0, 0. And then 90 over 11 minus 8 gives us 2 over 11. Minus 30 over 11 plus 3 is 3 minus 3 over 11. Positive 3 over 11. 30 over 11 plus 0 is 30 over 11. Minus 60 over 11. 0 and 1. Okay. And now we want a leading one in the third row, so we multiply by 11 over 6. And we get this same matrix. And you know what? Make a bit more room here. Okay. And the only thing that changes in this one is the third row. So we get 1 in this entry, and then minus 2 over 11 times 11 over 6 is minus 1/3. And 13 over 11 times 11 over 6 is 13 over 6. And minus 70 over 11 times 11 over 6 is minus 70 over 6, or minus 35 over 3. And in place of the 1, we get 11 over 6. Okay. taking this matrix, to clean that up a bit, the next thing we have to do is eliminate everything above and below the leading 1. So we have 6 over 11 times row 3 plus row 1, 3 over 11 times row 3 plus row 2, minus 2 over 11 row 3 plus row 4. Okay, and what we get is 1, 0, 0. Then 6 over 11 times minus a third is minus 2 over 11, which cancels with this perfectly. Then we get 13 over 11 minus 2 over 11 is 11 over 11, or 1. Then minus 35 over 3 times 6 over 11 is minus 70 over 11, plus 15 over 11 is 55 over 11, minus 55 over 11, which gives us minus 5. And this is 1 and 0. Okay, row 2, we have 0, 1, 0, and then 3/11 times minus a third is minus 1 over 11, so we get 0. Then we have 39 over 66 minus 1 over 11 is 6 over 66, so it's 33 over 66, which becomes 1/2. And then we have minus 35 over 11 plus 2 over 11 is minus 33 over 11, or minus 3. Then this 3 over 11 times 11 over 6 is 1/2. So we get 1/2 here and 0. Okay, next row stays the same. Okay, final row gets an additional, we eliminate this entry, and then we have 2 over 33 plus 3 over 11 is 9 over 33, so it's 11 over 33, or 1/3. Then we get minus 13 over 33 plus 90 over 33, so that's 77 over 33, or minus 7 over 3. Actually, no, it's positive 7 over 3. Okay, and 70 over 33 minus 60 over 11, or minus 180 over 33. That's 110 minus 110 over 33, or minus 10 over 3. Okay, and then we have minus 1 over 3 and 1. Okay, so this is the next step of the Gauss-Jordan elimination. And we just have to get one more step on this page. We're gonna just, let's put this over here, why not? Right here, all we really need to do is multiply this by let's do it like this. Okay, and this goes here, and we're just multiplying this row by 3. So we do 3 times row 4 gives us 1, 7, minus 10, minus 1, and 3. Okay, and now what's left? We just have to eliminate the row immediately above. So it's 1/3 of row 4 plus row 3. And the answer here will be so actually let's hold on to that and let's just do a new row here where we have the extra entries here. Okay, so we are canceling here, so we have 0. 7/3 plus 13/6 is the same as 14/6 plus 13/6, or 27/6, which is the same as 9/2. Okay. Minus 10/3 plus minus 35/3 is minus 45/3, which is minus 15. Minus 1/3 plus 11/6 is minus 2/6 plus 11/6, or 9/6, which is 3/2, and 1. Okay, so at long last, this is A inverse for the A that we started with. Okay, so even with a large matrix where the computations are difficult, we still eventually get to the inverse matrix we're looking for. Okay, I'll put a little A inverse here. Okay, so we've done some inverse matrix computations. Now let's state a theorem about inverse matrices. So if we have a square matrix A, which is n by n, then the following are equivalent. So if any one of these are true, then all of them are true. If any one is false, all are false. Okay, so first, A is invertible. That means an inverse exists. Second, the matrix vector equation, A times x equals the 0 vector, has only the trivial solution. In other words, x must be equal to 0. Third, the reduced row echelon form of A is In. It's the n by n identity matrix. So we'll recall that that's 1s in the diagonal and 0s everywhere else. Ax equals b. So this is a different matrix vector equation where instead of 0 on the right-hand side, you have some vector b. That's consistent for every n by 1 matrix B. And fifth, Ax equals b has exactly one solution for every n by 1 matrix B. So to be consistent, that means that a solution exists, whereas this is more specific. There has to be exactly one solution. Okay. And so now we're going to prove these statements. If you haven't seen proofs before, don't worry about getting bogged down in it, but it's just explaining why these things are actually equivalent. And the structure of the proof will be to prove that 1 implies 2, which implies 3, which implies 1. And that says that they're all equivalent because, you know, let's say 2 is true, that means 3 is true and 1 is true, just following the arrows. Similarly, we'll prove that 1 implies 4, which implies 5, which implies 1 again. And this is how it's done in our textbook in Anton and Roers. Okay, so let's start off. So suppose A is invertible. We'd like to show that Ax equals 0 has only the trivial solution. Well, what does it mean for A to be invertible? That means that A inverse exists. But what does A inverse do? We can multiply on both sides of this equation. Equals A inverse times 0. On the left-hand side, we can regroup this by the associative property to get A inverse A times x. On the right-hand side, any matrix times the 0 vector is going to be equal to 0. Just thinking about how matrix multiplication works. Meanwhile, on the right-hand side, we know A inverse A is the identity matrix. So this is just going to be IN times X. But we know that the identity matrix just gives you back the vector you started with. So that tells us that X is equal to 0. Okay, and so if AX equals 0, then X itself is equal to 0 by this chain of reasoning. Okay. Okay, so now that proves 1 implies 2. Now we can prove 2 implies 3. If AX equals 0 has only the trivial solution, then the reduced row echelon form of A is IN. Okay, so if AX equals 0 has only the trivial solution, that means that through some manipulations, possibly by way of Gauss-Jordan elimination, I'm going to arrive at the conclusion that x1 equals 0, x2 equals 0, etc., and xn equals 0. But that tells me that, and this is on the augmented matrix, I should say. On the augmented matrix, A0. Okay, but then, so if x1 equals 0 through xn equals 0, what that means is that this Gauss-Jordan elimination gets me to a matrix that looks like this, with zeros here. But that means that if I was just focusing on the left-hand side of that, on just A, that means that A reduces to the identity matrix via Gauss-Jordan. Okay, so looking at left part shows that RREF, the reduced row echelon form of A, is the identity matrix. Okay. 3 implies 1, that if we have the reduced row echelon form of A is IN, then just as we did before, if we start with A and then 1 with a bunch of zeros, this will reduce to IN, because that's the reduced row echelon form, with the first column of a suitable inverse matrix. Okay, so column 1. Okay, etc. And we can use this to construct an inverse matrix. Okay, and by way of that construction, we are able to show that A is invertible, since an inverse exists. Okay, so that completes the loop that 1 implies 2 implies 3 implies 1. To go through 1 implies 5 implies 4 implies 1, we're going to have start with the fact that A is invertible, and we want to conclude that AX equals B has exactly one solution for every n by 1 matrix B. Well, it's the same proof as before for just having the trivial solution when B equals 0. You just start with AX equals B, and then you multiply both sides by A inverse. And regrouping on the left-hand side, we know that A inverse A is the identity, which just gives you back the vector you started with, which is A inverse B. But that tells me that X, because A inverse exists, X can be given just by the formula A inverse B, and that must be the value of X. Okay, so this uniquely specifies X. Okay. So next we want to show that 5 implies 4. So if AX equals B has exactly one solution for every n by 1 matrix B, then AX equals B is consistent. Well, if you have exactly 1, that means that you have at least one. So this is kind of obvious. Exactly one implies at least one. Okay. As for 4 implies 1, if Ax equals b is consistent for every n by 1 matrix B, then A is invertible. Well, here we can use the trick from before. We'll start with Ax equals 1, 0, 0, and obtain the special matrix X. So the solution for X will be our C1. Okay, and then Ax equals 0, 1, 0. This will be the solution. The solution of this equation, which must exist by the fact that Ax equals b is consistent, tells us that the solution will be C2, and you can use this to construct your inverse matrix. Inverse using these columns. Okay, same as above. Okay, so that tells me that these 5 facts, which don't seem all that similar, are actually equivalent logically. Okay, so we've spoken a lot about invertible matrices and conditions that are equivalent to being invertible, but what happens if a matrix is not invertible? What would happen when I tried to do this procedure? So here's an example of a matrix A, which I'm giving you the hint, it's not going to be invertible. So what happens when we try to construct the inverse? So we follow the typical procedure. We write the matrix, and then we augment with this identity matrix. Okay. And then I try to carry out Gauss-Jordan elimination. So the first thing I do is add minus row 1 to row 3, and I obtain the same matrix on the top 2 rows, and then 0 and minus 4, minus 4, minus 1, 0, 1. And next up, I want to multiply this by a half, which gives us 1, 2, 3, 1, 0, 0, 0, 1, 1, 0, 1 half, 0. And this stays the same. Okay. Next, we want to cancel using the new leading 1. So we're going to add minus 2 times row 2 to row 1, and 4 times row 2 to row 3. And what we obtain is 1, 0, 1, 1, minus 1, 0. This row stays the same. And when we add this row, we get 0, 0, 0, minus 1, 2, 1. This entry is a problem for us because we're supposed to turn that into 1, but right now it's 0. So that tells us that this matrix A is not invertible. Okay, and it also doesn't satisfy the other conditions from this set of equivalent conditions. So the matrix AX equals 0, we'll see that that can have more than just the trivial solution. We know that the reducer echelon form of the matrix is not the identity matrix because we're doing Gauss-Jordan elimination, and we we're missing that bottom right 1. As for the 4th and 5th entries, you would be able to find that there are vectors b for which this matrix equation will not be consistent. Okay? So given that with this matrix A, the system is not always consistent, when will it be consistent? So here we're going to use the Gauss-Jordan elimination on the augmented matrix as before, but we're going to keep things symbolic, right? We're going to have B1, B2, and B3, and kind of see what happens as we do the Gauss-Jordan. So we have 1, 2, 3, 0, 2, 2, 1, minus 2, minus 1, B1, B2, B3. Okay, so as before, we start by taking minus row 1 plus row 3 and obtaining 1, 2, 3, B1, 0, 2, 2, B2, and in the final row we have 0, minus 4, minus 4, B3 minus B1. Okay. Now, as before, we want to multiply this row by 1/2. Okay. And again, we make sure to do this as well with our symbolic entry. So this is 1, 2, 3, B1, 0, 2, 2, sorry, multiplying by 1/2, 0, 1, 1, 1/2 times B2, and 0 minus 4 minus 4, B3 minus B1. Okay, what's up next? We need to take minus 2 times row 2 plus row 1, and 4 times row 2 plus row 3. Okay, so we get 1, 0, 1, and then minus 2 times 1/2 B2 is minus B2, plus B1 is B1 minus B2, then 0, 1, 1, 1/2 B2, 0, 0, 0, and this is B3 minus B1 plus 2 times B2. Okay, so this is where we arrived at the problems before. In general, when we have a matrix, an augmented matrix like this, the way that we can tell that this is consistent, so this is consistent if the whole bottom row is just 0. Okay? So in our case, what that means is that B3 minus B1 plus 2B2 must be equal to 0. Okay? So for consistency of AX equals B, this equation must be equal to 0. Okay, so some examples of vectors that would work for this would be 1 and 0 and 1, or 0 and 1 and minus 2, or 0 and 2 and 1. Okay, these would all be examples of vectors for which the system would be consistent. On the other hand, vectors B for which the system is inconsistent, the system include, here we have vectors like 1, 0, 0, 1, 1, 1, 1, 2, 3, basically a lot of vectors. So there are a lot of vectors which do satisfy, but in a certain sense, there are many more vectors for which this system is going to be inconsistent. Okay, so hopefully we got a taste of matrix inverses and how to construct the matrix inverses, as well as determining when a matrix inverse does not exist and how that relates to the consistency of linear systems. And I'll see you all for the next lecture. Thanks.